right, I've got another nonlinear system on the board. What I want to do is find the equilibrium solutions. We're going to pick one of them. We're going to find the linearized system that approximates that. Okay. And then we're actually going to draw the full phase portrait for that linearized system. And that's because this example is done in the book, so we can kind of cheat and look in the book for the phase portrait for the nonlinear system and compare that to the phase portrait we get for the linear system, because I want to point out some connections. Okay. So first thing is, if I'm looking for equilibrium solutions, I know that both of these need to be 0. So negative 2x plus x squared equals 0, and negative 3x plus y plus 3x squared has to equal 0. Now this first one's kind of nice. I can factor out a negative 2x, and I get times 1 minus x equals 0. So that's going to tell me that either x is 0 or x is 1. Now this equation is a lot more gnarly to work with on its own, but I know that this one also has to be true. So I'm just going to say, case 1, what if x is 0? Now if x is 0, this becomes 0 plus y plus 0 equals 0. Y would equal 0. The origin's an equilibrium solution. My other possibility is that x is equal to 1. If x is equal to 1, this becomes negative 3 plus y plus 3 equals 0. Once again, we get y equals 0. So 1, 0 is the other equilibrium solution. So this particular nonlinear system has exactly 2 equilibrium solutions, and one of them happens to be the origin. I'm going to go ahead and try to classify the one at the origin. Now, that means that in going from the xy plane to the uv plane, I'm not actually moving anything, because 0, 0 is going to stay at 0, 0. That doesn't mean we don't switch to u and v. X and y are the variables for this nonlinear system. The phase portrait in the xy plane is going to look different from the phase portrait in the uv plane where we have a linear system. Okay. So anytime you're doing a linearization, you do need to switch variables. Okay. So I know that what we're going to get is u prime v prime is equal to some matrix, it's the Jacobian matrix, times uv. And the connection between them here is that u is x and v is y. So they're going to take on the same values, but they're going to be variables for different systems. Okay. I'm going to just give this function a name. I'm going to call that f of xy, and I'll call this one g of xy, because then I know that the components of my Jacobian matrix are the partial of f with respect to x at the origin, because that's the equilibrium point I'm working with. These are the xy values. I'm still viewing this as a function of x. The number I get becomes the entry in the matrix for the uv plane. Partial of f with respect to y at the origin. Partial of g with respect to x at the origin. Partial of g with respect to y at the origin. And again, if it were a different equilibrium point, I'd be plugging in that equilibrium point. All right, let's see what this is. Partial of f with respect to x. Looks like I'm going to get a negative 2 plus 2x. So the partial of f with respect to x at the origin is just negative 2. Partial of f with respect to y is 0 everywhere, because there are no y's in here. So if it's 0 everywhere, then in particular, it's going to be 0 at the origin. Partial of g with respect to x. So I'm going to get negative 3 plus 0 plus 6x. Partial of g with respect to x at the origin, then, is just going to be negative 3. Partial of g with respect to y is going to be 0 plus 1 plus 0. That's going to be 1. And of course, if it's 1 everywhere, then in particular, it is 1 at the origin. Okay. So these 4 numbers that I calculated are the entries of my Jacobian matrix. I'm going to go ahead and just fill those in here. So we've got negative 2, 0, negative 3, 1. Excellent. So let's take a look at finding our eigenvalues. So if I look at j minus lambda I, that's going to be negative 2 minus lambda, 0, negative 3, 1 minus lambda. If I take a look at the determinant of j minus lambda I, that's going to be 2 minus lambda times 1 minus lambda minus just 0, which is great. So I'm not going to multiply that out because my characteristic equation then is just that this product is equal to 0. But that tells me that lambda is 2. I'm sorry, that was a negative 2. My bad. This should have been a negative here and a negative here. And so that's going to make lambda equal negative 2. Or lambda is going to equal 1. So I know right now we've got a saddle. And that's one of the cases where this works. So the origin is a saddle in both the linearized and the nonlinear system that we have. All right, but I want to get a phase portrait in the UV plane. So I want to find my eigenvectors that correspond to my eigenvalues. So let's see, I think I need to have J written down somewhere just so I don't lose it. Okay, so if lambda is negative 2, I can look at J plus 2I, and that's going to be 0, 0, negative 3, 3. So we're trying to solve this lovely system that this matrix times an arbitrary vector, non-zero vector, is going to be equal 0. So I get 0 v1 plus 0 v2 equals 0. That's always true. Negative 3 v1 plus 3 v2 equals 0. v1 equals v2. So I'm going to just choose them both to be 1. So I will get 1, 1 is an eigenvector corresponding to lambda equaling negative 2. So let's take a look at lambda equaling 1. If lambda equals 1, I'm taking a look at j minus I. And j minus I would be negative 3, 0, negative 3, 0. So we're trying to solve this system. I'm just going to use w's this time. So negative 3w1 plus 0w2 equals 0. Negative 3w1 plus 0w2 equals 0. That tells me w1 has to be 0. w2 is free to be whatever I want. So I'm just going to let w be 0, 1. That's an eigenvector corresponding to 1. So now with this, I can pretty nicely draw in the UV plane what my phase portrait looks like. I know I've got an equilibrium solution at the origin. 0, 1, which just puts me on the y-axis, is an eigenvector corresponding to 1. So the y-axis is going to give me straight line solutions that are moving away from the origin. And then the vector 1, 1, so over 1, up 1, that's going to give me straight line solutions that are approaching the origin. And so, of course, I'm getting a beautiful saddle, like so. Excellent. Now, this example is worked out to some extent in your text. It is actually on page 468. And what they do is they show you the phase portrait for the nonlinear system that we started with, and then they sort of zoom in near the equilibrium points. Remember, we said the origin was an equilibrium point, and there was another equilibrium point over here at 1, 0. Now, there are these straight line solutions here. So that's 4 different curves, because each half line is a solution curve that approach or leave the origin. We don't lose that. We're still going to have 4 curves, 2 of which go away from the origin and 2 of which approach it. The difference here is that they don't have to be straight lines. Now they can be. It looks like for this system, the 2 that are moving away actually are straight lines, but the 2 that are moving towards it are not straight lines. Okay. All right. And then they just draw in some other curves to sort of show what's happening. Stuff like so. And it gets kind of interesting. Over here, it's really looking very similar to what we have over here. Over here, there's this other equilibrium point. And this other equilibrium point happens to be a source. And so the solution curves start moving away from that. So once you get over to where the other equilibrium point dominates, it no longer looks like a saddle at all. One vocabulary word that goes along with this is a separatrix. Now we've seen that before. When we had a linear system, we said the separatrices were the straight line solutions that corresponded to the negative eigenvalue. And that's because you can sort of see solution curves on either side of that have drastically different behavior. Whereas for the positive eigenvalue, solution curves on either side actually have fairly similar end behavior. Okay. Over here, all 4 curves that approach the equilibrium point, in this case, which is the origin, as t goes to either plus or minus infinity, count as separatrices. Okay. Now, for this particular example, it still looks like the curves that are moving away from the origin don't really separate into different behavior. But suppose that there was another equilibrium point over here. Now there's not, but in theory I could have something that had a phase portrait like this that had a third one. A solution on this side of that straight line solution might get caught up in that equilibrium solution, and this might get drawn farther away. So it's possible that any of these solutions that either approach the origin as t goes to infinity or go away from the origin, meaning they're approaching as t goes to negative infinity, any of those could divide things up into things that have drastically different end behavior. They don't have to, but they can. If it's a linear system, I kind of know that the ones that move away from the origin don't drastically change the end behavior of solution curves that are nearby. If I have a nonlinear system, any of those curves that approach the origin as t goes to plus or minus infinity could potentially, although they don't necessarily, divide the solution curves on either side of it into having drastically different end behavior. And so we call all of those the separatrices. Okay. Again, this is on page 468 of your text. I will admit the picture in the book is a little bit better than mine, so I'd encourage you to take a closer look at that.